Hey everyone, Mr. Fransky here. Today we're going to talk about logarithmic differentiation. This is a technique we use when we have an x in the base and in the exponent. So we're going to be able to find complex derivatives by using logarithmic differentiation. Vocab, pretty standard stuff: log properties, product rule, implicit differentiation, and of course logarithmic differentiation. So first I want to talk about some of our log properties and how they're going to help us in doing these problems. So remember, if we have a product of a function or anything inside of a log, we can break it up into addition. If we have a quotient, we can change that to subtraction. This comes from the exponent rules. And if we have an n, we can throw it to the front. That is n log base b of x. Log base b of b, that really, if you think about bumping this over, b to the first is indeed equal to b, right? That makes sense. B to the 0 is 1, that makes sense as well. And b to the n equals b to the n. So if you think about bringing this over and bumping it, not a big deal. You can also move it to the front. Log base b of b is still 1, n times 1 is n, however you want to think about it. I do this slide also in the exponential and log derivative review video as well. So if you already saw it, you feel free to skip this, but this just, I think, is helpful for some of the problems we're going to do. Natural log of e, there's an e hiding down there, so that's just property number 4. It's just 1, right? E to the first power is e, not a big deal. E to the second power is e squared, so that's 2. That's kind of like rule number 6, right? This is kind of like that too, but it's hiding there. E to the 1/2 for the root, right? So that's 1/2. 1 over e, that is e to the negative first power, so that's negative 1. Natural log of 2e. At first glance, this might look like we can't do anything with it, but let's look at property number 1. That's ln of 2 plus ln of e. Well, ln of e is 1, right? So this is 1 plus ln of 2, or ln 2 plus 1, either way you want to do it. Next one, this one's kind of interesting. There are a couple ways to do it. One is you have ln e to the 4th minus ln of e to the 7th. Well, that is just 4 minus 7, which is negative 3. Or you could have looked at this and said, well, e to the 4th over e to the 7th, that is e to the negative 3rd power, or 1 over e cubed. That just automatically gives you negative 3. Either way, all the same thing. All right, so when do we use logarithmic differentiation? This is important. You only do it when there's an x in the base and there's an x in the exponent. Now, you can really do logarithmic differentiation on any of the problems we've done with an exponent, but my question would be why? Because we only want to do it on problems where we have to. But like if you have derivative of something like, I don't know, x to the 4th. We know that's 4x cubed, right? You don't have to do logarithmic differentiation on that. That's the power rule. X to the n goes to n x to the n minus 1. Derivative of a to the x, like let's actually do it with a number. Let's do like 2 to the x. That is 2 to the x, leave it alone, times ln of 2. We know how to do that as well. Could do log differentiation on that, but not that important. Okay, so we don't really have to think about doing that. And in general, a to the x, right, goes to a to the x times ln of a. That includes e. If it's e, it's just e to the x, ln of e, but ln of e is 1. So let's check this out. The way I always do this is, all right, y equals x to the x. Now I take the natural log of both sides. Always. If you have x in the base and the exponent, you have to do this. Now the x I can bring to the front. Now I don't have that x to the x issue anymore. Now on the right I have a product of functions. On the left I have a function of y. So we're going to have to use implicit differentiation. So 1 over y times y prime, that's the derivative of the left side, equals 1 times ln x, that's the derivative of x, plus x times 1 over x. Ah, that's 1. That's nice. So we have y prime equal to y times ln x plus 1. Now this y is pesky. You don't want it there, but we have a formula for y. So this is equal to x to the x times ln of x plus 1. And that'll give you the slope of the tangent line at any point that's on x to the x power. Cool. Let's try another example. Ooh, fun. Got some trig. So 1 minus 3x to the power cosine x. So if we do now y equals 1 minus 3x to the power cosine x. Natural log of both sides. Natural log of y equals natural log of 1 minus 3x to the cosine x. Cosine to the front, so we have natural log y equals cosine x times ln 1 minus 3x. Now notice at this point I have done no derivatives. All I've done is move stuff around, take natural log of both sides and move that cosine to the front. Now we take the derivative of both sides. 1 over y times y prime. Derivative of cosine is negative sine x times, leave the ln of 1 minus 3x alone, plus, excuse me, this time leave the cosine alone, multiply by the derivative of this guy, which is 1 over 1 minus 3x. Now we have to chain that, right, times the derivative of the inside function, which is negative 3. So y prime is y times negative sine x ln 1 minus 3x. Let's see, minus 3 cosine x over 1 minus 3x. I think that's the best we can do. Okay, now we know y. Y is 1 minus 3x to the cosine x. So y prime is 1 minus 3x to the cosine x multiplied by negative sine x ln of 1 minus 3x. 1 minus 3x minus 3 cosine x over 1 minus 3x. There we go. It's a mess, but it's right. And really no hard math in there. You just got to do it. You just got to keep plugging forward. That's kind of the moral. All right, I think I got one more. Yeah, this is a fun one. We got a 1 over x, we got a secant x squared, all kinds of chain rules going to be happening here. Yeehaw. Let's give it a shot. So we have y. This is our function for y, so take the natural log of both sides. I'm going to take a little shortcut here. I'm going to move the 1 over x to the front right away. It's just going to save me one step. So we got natural log secant x squared. Okay. So now take the derivative of both sides. 1 over y prime. You're probably noticing that pattern. It's always 1 over y prime. Derivative of 1 over x. 1 over x is x to the negative 1. So that's going to be negative 1 x to the negative 2 times natural log secant of x squared. Plus, now leave the 1 over x alone. Multiply by the derivative of natural log of secant of x squared. That's going to be 1 over secant x squared times secant tangent of x squared. So secant x squared tangent x squared times derivative of x squared, which is 2x. Hey, that secant x squared just cancels. That's nice. And then we got a 2x, so that x is going to go away. And so what do we have here? Let's rewrite it pretty. So we got y prime is y. Let's bring it to the other side. Negative 1 over x squared times natural log secant of x squared plus tangent, 2 tangent of x squared. I think that's the only thing that's left on the right over there. Okay, so y prime, what's y? Y is secant of x squared to the 1 over x. And then that's multiplied by negative natural log secant x squared over x squared plus 2 tangent x squared. Whew. Fun. Not terrible, though, right? Just got to keep plugging forward. So let's do a little summary of the derivatives we have with exponents. So a to the b, notice there's no x there. They're asking for the derivative with respect to x. This is a constant to a constant, so it's 0, right? That'd be like the derivative of pi to the third, right? Oh, it's not 3 pi to the 2. It's just 0 because it's a constant. Next up, we got the derivative of x to the n. We use power rule for that. X n to the n minus 1. Derivative of a to the x. Leave the a to the x alone, just like if it were e to the x, then we multiply by ln a, excuse me. If it was e to the x, it's ln of e, and it would just be nothing there. X to the x, we just did this one. It was x to the x times, what was it, ln x plus 1? I think that's what it was. Let me double check. Ln x, yep, plus 1. And we did that by using logarithmic differentiation. Okay, so when do you use logarithmic differentiation? Only when you have an x in the base and also in the exponent. Okay? All right, so nothing too tough in there, hopefully. I love you guys. That's why I'm here. Have an excellent day.